Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hilmi bin Zulkifli. My major ID is MA1941. Okay, for fluids mechanics project, I will present the introduction and the background of the project. Okay, for the introduction, aerators is the various mechanical device used for aeration or mixing air with another substance such as soil or water. The device purpose is to add oxygen in the water and it widely used in an aquarium tank and many more. So the background, Bernoulli equation. The Bernoulli equation is an approximate relation between pressure, velocity and elevation, and valid ingredient of steady, incompressible flow where net frictional forces are negligible. The Bernoulli equation also is valid only in the inviscid regions of flow where net viscous force are negligibly small compared to initial gravitational or pressure force. The equation is obtained from the conservation of linear momentum for a fluid particle moving along streamlines. As you can see, this is the Bernoulli equation. This is the derivation of the Bernoulli equation. It has come from three different formula, which is dV over dt2 equal to dV over dt1. So we derive it dV over dt, which is the amount of fluid per unit time. 1 equal to amount of fluid per unit time 2. Okay, we get d times a times x1, which is the distance, divided by delta t, and d times a2 times x2, which is distance 2, divided by t. So we will get a times a1 times v1 equal to a2 times v2. Hence, this is the formula density, which is mass equal to density times velocity. Also, pressure equal to force over A. So this is the work done. So work 1 is equal to F1 d1, which is force and distance. Work 1 is equal to P times area, which is force, formula of force, and d distance is x, amount of distance of fluid. Same goes to work 2. So we assume that work 1 is more than work 2. So when work 1 minus work 2 is equal the change of potential of energy plus the change of kinetic energy. So work 1 minus work 2 is equal m2 gh2 minus m1 gh1 plus half of m2 v2 squared minus half m1 v1 squared. So we derive it until we get the Bernoulli equation. As we can see, the Bernoulli equation is the constant. Left side is equal to right side. So we can get the P plus rho GH plus 1 over 2 times rho V squared is equal to constant. Next is limitation and application of Bernoulli equation. So the limitation of Bernoulli equation is steady flow. It is only applicable to steady flow. Next is no shaft work. It's not applicable in a flow section that involves a pump, turbine, fan or any other machine or impeller, since such a device destroy the streamlines and carry out energy interaction with the fluid particles. When this device exists, the energy equation should be used instead. Next is no heat transfer. The density of a gas is inversely proportional to temperature, and thus the Bernoulli equation should not be used for flow sections that involve significant temperature change, such as heating or cooling sections. Next is applications of Bernoulli equation. Bernoulli's principle can be used to calculate the lift force on an airfoil if the behavior of the fluid flow in the vicinity of the foil is known. Next is the carburetor used in the many reciprocating engines contains a venturi to create a region of low pressure to draw fuel into the carburetor and mix it truly with the incoming air. And lastly is incompressible flow density is taken constant in the derivation of the Bernoulli equation. The flow is incompressible for liquids and also by gases at Mach number less than 0.3. So that's all for me. Thank you.
Hello, my name is Irsyad bin Shukaimi. My matric number is MA19132, and Today I'm going to present on material and discussion of this project. So first, for the material of this project, I use bottles. This is the bottles of our project, and this is a 0.05 meter of pipe, and this is 0.08 diameter of pipe. Okay, and this all material that I use to do this project.
Assalamualaikum warahmatullahi wabarakatuh. My name is Kamal Haiqal, Matric ID MA19147. So I would like to present about the methodology and result for our Aerator project. So for methodology, the first thing first is we need to calculate the volume flow rate from the pipe itself. So we need to open the pipe with 1 full rotations and record the time taken for the water to fill 1 liter bottle, and we repeat 3 times for the average time taken for the water to fill the bottle, and we repeat the process for 2 and 3 full rotation of pipes. Secondly, we need to calculate the volume flow rate by using the formula of Q equals to VT, where V is the volume of water and T is the time taken for the water to fill the container. Number 3, we set up the apparatus as figured shown below. As we can see, we set up a small hose between 2 containers to demonstrate the aerator. We can start the experiment by open the pipe with 1 full rotation while connected to this aerator itself. And we can record the observation, which is we need to observe if there are any air bubbles in the aerator. And we can repeat the experiment with a complete 2 and 3 rotation of pipe while connected to the aerator. So for the result, before anything else, we need to measure the diameter 1 and 2, which is the inlet for the aerator. So for diameter 1 we get 0.08 meter and diameter 2 is 0.005 meter. We assume that the density of water is 1000 kg per meter cube. And from the diameter we can calculate the area of inlet by using the formula of pi r square. As the table below, we can see that we have calculate the average time taken for each turns of pipes for the time taken for water to fill the bottle. And before starting with our main objective, we need to calculate the velocity of fluid by using the formula Q over A, where Q is our flow rate and A is the area of inlet. From the observation below, we can see that when 1 full of rotation, only small bubble form inside the aerator, but in 2 full rotation of pipes, moderate bubble forms in the aerator. And lastly, in 3 rotation of pipes, the bubble form rapidly inside the aerator. We can also observe that the pressure inside the aerator is also increasing with respect to the number of turns of pipes. So we can conclude that the faster the water flow, the higher the pressure. So that's all from me. Thank you.
Okay, so let's now talking about discussion of this project. So there was a part of this project where there was the water being flowed to this part of the bottle throughout, and there was a bubble formed at this pipe and go out of these bottles. There was a bubbles there. So there's based on the turn of the pipe, the number of the bubble increase based on turn of pipe. Okay, so we look up on some error that occurred during this experiment, during this project, which is the first one is we cannot estimate exactly the flow of the water based on the turn of the pipe, so we cannot get the perfect result based on that. So to overcome that, we must use the proper equipment at lab. Okay, so the second one is the material of this project. This project is not too suitable to see the bubbles, and the bubbles cannot form perfectly. That's all for me. Thank you.